In this video, I am going to cover the theorem which help you to analyze your electric circuits. The first theorem, Thevenin's theorem. The statement of your Thevenin's theorem is any linear lumped bilateral network with two terminals can be replaced to an equivalent circuit consisting of the voltage source in series with the resistance. Thevenin's theorem and then Norton's theorem, both are same procedure we are going to follow. A small modification is required, so we will see later. In the Norton's theorem, any linear lumped bilateral network with a two terminal can be replaced or reduced to an equivalent circuit consisting of a current source parallel with the resistance. In the Thevenin's theorem and then Norton's theorem, both the resistance, finding the equivalent resistance or same. So here R Thevenin, here Rn. So here we represents the Thevenin's resistance RTH, that is nothing but your Rn. So some textbook they will represents the Rn. So finding the R Thevenin Rn is same procedure to be followed for both the theorems. After that, so what here the Thevenin's theorem says that any type of linear network, so it's not any type, it's a bilateral network. So this theorem only applicable for the bilateral network, not a unilateral. So keep it mind, bilateral network. And then any number of resistors arrangement that has to be converted into a single sources connected with a single resistant branch. That's the theorem power. So if you have a bulk circuit, two three sources connected, and then 5 6 7 resistors arrangements are incorporated in the network, that entire network I'm going to replace with a single source with a resistor. That's the theorem power. So here what I'm going to do is, in the Thevenin's theorem, that such a type of circuit I'm going to replace with the single voltage source resistor connected in the series. The same way I'm going to measure the single current source resistor connected in the parallel. So here voltage source is the Thevenin voltage, or sometimes they may be called as a open circuit voltage, because we are measuring the Thevenin voltage at the condition of open circuit. So where we are measuring, that point is the open circuit, VThevenin or open circuit voltage. So next one, current source, Norton's theorem. Sometimes they may be represent ISC, short circuit current. Here we are going to measure the current which is the short circuit in the terminal, short circuiting the path. That's your Norton's theorem. So next, another two more beautiful theorem, superposition theorem, then maximum power transfer theorem. In the superposition theorem, so in any linear lumped bilateral network which is energized by two or more sources, the voltage across or the current through any of the resistor or source may be calculated by adding algebraically all the individual voltages or current caused by this separate independent source acting alone, with all other independent sources are removed. That's your statement of your superposition theorem. So nothing but, if three sources acting simultaneously, your load has give some response. That response is, we are going to measure by activating the source, one source at a time. So first source, if I'm going to activate, what is the response I'm going to measure the load. Second source, I'm acting alone, so what is the response. Third source, I'm acting alone, activating alone, what is the response. If I'm going to add the algebraic sum, so not a sum, it's an algebraic sum. Sometimes if you are going to measure the current, that the current direction may be changed plus or minus. So algebraically sum, you will get a resultant response. That resultant response is equal to all the three sources are activating at a time. That is your solution theorem. So maximum power transfer theorem, which help you to how our energy, source energy, maximum converted or transferred to the load. That is your maximum power transfer theorem. The maximum power is transferred from source to load when the load resistance is equal to source resistance. Not a load resistance, it's a source resistance. So whenever you are matching with your load resistance with your source resistance, at the time your maximum energy of your source is transferred to your load side. That is your maximum power transfer theorem. Yeah, steps which we are going to follow for the Thevenin's and Norton's theorem. As we know that Thevenin's and Norton's theorem, both we are going to replace the entire circuit into a single source connected with the single resistance, right? So how do we calculate that single resistance connected in the series and parallel manner? So here the represents Thevenin resistance, that is nothing but your Norton's resistance. If there is a circuit in the circuit terminal AB, so there we need to asking to find the open circuit voltage or short circuit current. So at the time I'm going to replace that particular resistance and then remove my all sources. If there is a voltage source, I'm going to short circuit. If there is a current source, I'm going to open it. After that, looking back from the terminal where we removed the load resistance, looking back from that terminal AB to find the equivalent resistance, that is your Norton's resistance or Thevenin resistance, right? So after finding the R Thevenin and RN, so we have to go for finding the open circuit voltage and then short circuit current for Thevenin's and Norton's theorem. For the open circuit voltage, I am again consider it for the original circuit without connecting the load resistance. In this place, load resistance removed, so openly its circuit is in open condition at the time. So what is the potential between the terminal AB? That is my open circuit voltage or Thevenin's voltage. So now, as we know, V Thevenin or Thevenin, so entire circuit is replaced with a single voltage source series with a resistor, right? I am bringing the original circuit. The terminal AB is removed with your load resistance is already removed. What I am going to do is I am going to short the path of terminal AB. So at the time, so I am going to measure the current flowing through the shortest path, short circuit path. That current is my Norton's current. So Norton's current parallel with your orthogonal. So in this case, the entire circuit is replaced with the current source parallel with the resistance. So these theorems we will see in the next video with an examples. Thank you.